Hi, Kara. Hi, Kara. Can you hear me?
Sí.
Okay. Okay. How we doing, guys?
Good.
Okay.
Great.
Do we need to talk about the notebooks?
Yes, please. I wanted to ask if I was able to talk to you at the end of the class because I guess I don't get it. I guess I'm not writing it right. I really don't know what is happening.
Okay, Veronica, what have I said in your notebook? Have you been able to access the comments?
Yes, I have, but like one of the comments was I don't see the calculations. I know that the last class after
You don't,
after I
I'm sorry,
sent,
I didn't hear you. You don't see the what, Veronica?
it says that you don't see the calculations for the problems, and then they are
Did
right
you,
like
Veronica, did you make a separate section of them?
no.
No? Well, that's the problem. Okay. Veronica,
But the calculations were
I do not, I don't care. Veronica, sometimes you have, even though it may seem unreasonable, and this may seem unreasonable to you, the fact is, I want a separate section with the calculations. If you keep on giving me the calculations within the data table, I'm going to continue to say no calculation section and mark you off for it.
I mean, it was not with the data table, it was with the answers at the end, but okay.
I want a separate section labeled calculations, calculations following. I can't be more clear than that.
No, yeah, I understand. There were other couple of things, but I don't have
Okay,
the
that's fine.
document.
Veronica, if you want to stay, we can go through it together. I don't have any problem with going through it together.
Okay.
I've already eaten tonight, so I'm good there. I just, I'll be happy to stay here as long as you want. Well, limited speaking, I got to get up at 5 o'clock for a doctor's appointment tomorrow. But other than that, I'll stay for a long time because believe me, guys, you know what's going to happen once you guys learn how to do this? I'm going to just see that you've submitted and I'm going to start going and doing nines the whole time. The only time you're going to get points off once you learn how to do this, right? The only way you're going to get points off is if you don't submit it. Okay, do it right once. That's all I'm asking. Just do it right once. I need to have you show me you can do it right once. I've already given somebody in the, anybody who knows Faye Aiken, she's already gotten a 9 for me. As long as she submits reports from here on out, she is good to get 9s the whole time. Believe me, I don't want to do this hassle. Other questions about the notebooks?
How do we see like our past notebook uploads and your comments?
You should be able to just access the Dropbox. Can you, Madison, can you access the Dropbox?
Figure that out.
I also went to grades and I just went straight to the lab books right at the bottom, and you can click and see your submissions and see his little comments in. And you can see every single one that's been uploaded since the beginning. So that's what I do. So I can just click them right down the line.
It's on the top bar. There's like a thing that says submission review, and then you click that
too.
Click drop boxes, and then it has all the
Yeah, that too. I do grades.
Thank you.
Guys, sometimes you know more than I do. So I'm going to screenshot I think I'm on the right page here. Yes, I'm on the right page. Okay. So I'm going to submission review, correct? I'm in as a student. I'm going to submission review. I'm going to drop boxes, correct, guys? Talk to me.
Yes.
Okay, I'm in drop boxes. Ah, crap. I can't do this because I haven't submitted anything.
I figured it out, but it's usually right there where you are, where it says evaluation status. It'll say like feedback review.
I don't want to log out. Hold on one second. I'm going to get out of here. Okay, submission review, drop boxes. Okay. If I click on a Dropbox, right? As you seeing anything? Does anything look right? Kara, do you mind if I open yours? Kara,
Yeah, sure, sure.
does this look anything like what you're seeing, guys? Talk to me. Yay, nay?
It's still loading up.
No, I gotta. Oh, another thing, Kara. Do you know how hard it is to read things like this?
So actually there's, if you click control, the bracket, one of those brackets, it'll, pull it over.
Okay. I'm obviously, I'm not seeing this the way you are.
However, it's just when I take the pictures from my phone,
Okay, one second,
sometimes they don't upload the same way that they, when I print them out in, through my Adobe PDF, it sometimes doesn't come out the same way. So sometimes I have to mess around my camera to make it go the right way. But I think your other one should be fine.
Okay.
I have a question.
Yep, I have an answer.
Okay, so your comment on my last report was that you want a separate section for calculations, even if
On the
prompted
last
by the data
notebook.
table.
On the notebook, yes.
So on the actual data table, do you want us just to write the number answer and then
Yes.
have a whole other
Yes.
separate calculation section with the wording? Okay, gotcha.
Yes, exactly. That's exactly what I want. Because believe it or not, when you get some complicated data tables and you try and throw the calculations in there with it, it is very confusing to try and read. That is why I want a separate section for calculations. Any other specific questions about notebooks?
For
on.
the chemical hazards, I know on the last one you said just the unknown substance for the hazard once we determined what
Yeah.
it was.
Pretty much, yeah.
Okay, so it's normally just gonna be like 3 to
And
5
yeah,
tops.
you guys, for the density, there wasn't really one. So I for something like that, I just need to have you address it. If there are no chemicals that are hazardous, say no chemical hazards in this laboratory. That's all.
All right, thank you.
This laboratory, there should be only the copper chloride. That should be the only chemical you have for hazardous waste. Any other questions about the notebooks? Because I really want to get this thing nailed down. And I am sorry about getting them to you so late, but literally speaking, guys, I got so much grading especially because I had tests last week. I couldn't get to them before I did. I'm sorry about that. Anything else about the grading? All right, let's throw it somewhere else. How about lecture? How are you guys doing in lecture? You should be about on gas loss right now, if I'm judging correctly. If it were me, that's where I would be. Gas loss?
My
Yeah.
chem professor is taking a different route. We started going into quantum mechanics.
Okay, fair enough. Fair enough. How are you doing with that?
It's going. It's going. So I don't have a whole lot to say. I mean, I'm getting it slowly.
All you gotta understand is those shapes you see, the shapes that they draw out.
Actually, that part's easy.
Okay.
That part I get. The whole orbitals and the whole PD, that I could do in my sleep. It's just more on the when I get certain questions in the quantum mechanics, like determining the shortest frequency in order to eject an electron based on your given kilojoules.
Whoa.
That's where I kind of get a little.
Whoa.
That's where I kind of get a little weirded out because that's a two-step process.
Who's your
Okay,
professor?
Professor Selby? Yeah, Selby.
Yeah, okay.
Wow. Is he using the Rydberg equation with that or what?
No, we're not cut. I mean, we kind of briefed it, but we're not required to go into the Rydberg equation. So we're doing more on the frequencies, the de Broglie, what is it? The wavelength, energy, frequencies.
Well, you're dealing mainly with two laws there.
Yeah.
And that is E is equal to H nu, energy is equal to Planck's constant times the frequency. And the other is C is equal to frequency times the wavelength.
We haven't really got into nu, but we have done de Broglie's wavelength frequency, the one that you mentioned. And I know that we've been learning a little bit about the binding energy. So, yeah.
God bless them.
I wish it was gas.
I will be perfectly honest with you. I have not touched that stuff. I've not touched that stuff since 1977. That's the truth and a fact.
Yeah, now we're finally getting to some easier stuff where now we just need to know, where it's the ionization there, where the ionization goes. And that's easier.
So you're doing periodic trends then now?
Yeah, now we're finishing, we're kind of doing that quantum mechanics with the periodic trends, and then we're going to move on to something new. But the trends are that I remember from intro. That's easy.
God bless you. I don't know. I don't know what to tell you.
Well, luckily I don't need to know how to determine the electron affinity, so I'm good on that because I was freaking out with him on that one. So luckily, no, I get a chart.
Anybody else? Somebody bring me back to sanity. Anything else you're discovering?
My teacher's taking a whole other route. We just started moles and atoms and like converting from moles to atoms, moles to molecules, STP.
STP, you're doing gas laws then?
Yeah. And
Okay.
we're about to go to stoichiometry.
Okay.
My
Good enough.
professor's on chemical reactions and chemical quantities.
Wow, you guys are all over the place.
Yeah, we haven't even touched gases or solutions in aqueous reactions.
Are you okay with it? Anybody confused other than the person is dealing with de Broglie's law? Anybody else confused about anything? All right, good enough. See if I try and help you again. Seriously, if you have questions, that's why I try and open up here, all right?
I did have a
And-
question. I had a question on the fifth on the pre-lab for this week. I forget what it was, but it stumped me.
Okay,
Let me pull it up.
back to user, back to folder submissions. Pre-lab for empirical formula, correct?
Yeah.
Uh,
I think it was that one.
Who are you?
Brian.
I'm sorry?
Brian.
Brian. Okay, Brian, do you mind if I show your quiz?
Sure. Oh,
I'm gonna take it it's the one you got wrong.
yeah.
All right. All right, you're seeing it?
Yeah.
Okay. Oh. All right. God bless Dr. Musgrave. God bless him. All right, what he's doing. You normally, right? You're normally doing these things, these calculations, and you normally think, okay, I'm comparing the cation to the anion. So the cation always is going first. So the cation is going to be compared, is going to be the first number. The anion is going to be the second number, right? That's the way we normally do it. Right?
Yeah. Yeah.
All right. Read the question. He's asking you to do the chlorine first.
Yeah.
So in other words, you were right, but you put it backwards.
Okay. Because I was like, what? I thought it was. All right. Sweet.
Brian, you happy?
Yeah, I'm happy.
All right. Anybody have anything else? All right. So
We do that to mine?
who's mine? I don't know who you are. How can I do it to yours if you don't tell me who you are? So
I'm
the
Veronica.
answer to that is no. I can't do it because I don't know who you are.
I'm Veronica
Veronica who?
Bruseno. You know me, I'm the only Veronica in the lab.
Veronica, I will look into it.
Okay.
I will look into it and regrade the pre-labs. Okay?
Mhm.
Understand. The only way you're going to get the credit for it is if you answered 1 to 2 as opposed to 2 to 1. We fair on that, guys?
Yeah.
All right. Aisa?
Yes, sir.
Okay, I want you to get with somebody and you are not submitting your notebooks correctly. Okay, you need to submit them, I believe, as a PDF file. Do you think you can get with somebody in the class and figure out what you have to do?
Sure, I'll reach out.
Thank you very much, Aisa. Anybody have anything else while we're sitting here talking about things? So Aisa's here, Veronica's here, Kara's here. Cassandra, I think I saw you there, didn't I? Cassandra? Cassandra going once. Going twice. Madison, I saw. Ramiro, is Ramiro here?
Yeah, I'm right here.
Thank you. Did Cassandra chime in? Okay, Alex, I think I saw you. Tin, I saw. Mac, I saw you. Bell.
Here.
Bell, thank you, Bell. Victoria, I saw. Brittany, is Brittany here? I know I didn't see her yet. Brittany. Gracie. Grazie. And Brian, I got. Okay. All right, ladies and gentlemen, anything more that I need to get into before we get into the lab? By the way, how easy was last week's lab to report out? Piece of cake?
Very easy.
All right, the first half of this is the same thing as we did last week. All right. So I'm going to unshare this if I can find stop share. And I'm going to pop up the magical PowerPoint. All right, ladies and gentlemen, we are doing empirical formulas. Anybody know what an empirical formula is? What is it? I'm hearing crickets.
Is it the like smallest form of a chemical formula?
Kind of, sort of. You can think of it that way, yeah. It is the smallest whole number ratio of atoms within a compound. That's all it is. So if I am dealing with something like glucose, glucose is C6H12O6. So the actual number of atoms, the 6 carbons, the 12 hydrogens, and the 6 oxygens, that is the molecular formula for glucose. The empirical formula is the smallest ratio. So I can divide 6, 12, and 6 by 6, correct, guys? Good night?
Yes.
So if I do that, my ratio becomes 1 carbon to 2 hydrogens to 1 oxygen. So that gives me the formula of CH2O. That is the smallest whole number ratio of atoms in the formula. That is the empirical formula. Good enough? Cool bananas? We good? Come on, I need an amen.
Cool beans,
Yep.
cool beans.
Thank
Yes.
you, thank you, thank you. All right, now, to solve for an empirical formula. All right, let's think about this. If I had the ratio of 1 carbon to 2 hydrogens to 1 oxygen, and I have 1 molecule, that's what the ratio would be, correct? Right? If I had the ratio of carbon to hydrogen to oxygen would be 1 to 2 to 1, right?
Yes.
All right. Now, if I would multiply that by 6.02 times 10 to the 23rd, I would have 6.02 times 10 to the 23rd atoms of carbon times 12.044 times 10 to the 23rd atoms of hydrogen and 6.02 times 10 to the 23rd atoms of oxygen, right? Wouldn't I do that? If I multiplied everything, if 1 molecule was equal to 1 to 2 to 1, then 6.02 times 10 to the 23rd molecules would be equal to the numbers I just gave you, correct?
Yes.
So isn't 6.02 times 10 to the 23rd equal to 1 mole?
Yes.
Yes.
So in effect, if I have 1 mole of my glucose, I have 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. So all I have done is take my moles and determined what the molar ratio is amongst them within the compound. That gives me the empirical formula. The subscripts of the empirical formula are the molar ratio, which makes life really easy for us because all empirical formulas follow the same pattern. You find the masses of all the elements. That's the first step. That's generally the hardest step that you're going to have. Second step, you got to turn all of those masses into moles. Then once all the elements within the compound are in mole form, you find the smallest one, the smallest number of moles, and you divide all the other moles by that smallest number. What that does is that gives you the molar ratio, with one exception. Sometimes the smallest ratio involves a fraction. You can't have fractions in any chemical formula. You can't have half an atom. You can't have a third of an atom. So the fourth step becomes, if necessary, you have to use a multiplier, which you multiply all the molar ratios by to get whole numbers. That's it, guys. Every empirical formula problem you're doing is solved by these four steps. All right. We need to find the empirical formula of this compound, FeXBry.ZH2O. Remember, the Z stands for the number of water molecules that are related to the iron bromide molecules. So in order to do this by my strategy, I need to find the masses of the water, the Fe, and the Br. Water's easy. We did that did we not do that last week, guys? How did we determine the weight of water in a hydrate last week?
Divided by the total mass or something. Right.
That gave me the mass percent.
Isn't that we just extract the two numbers?
We weighed the hydrate before we started. Then we heated it up, drove off all the water, and we weighed it again. The difference of the two is going to be the weight of the water. We did that last week, right? We did it last week. It was good enough for us then. It's good enough for us again this week. We're going to do it again this week. So we take my crucible. My crucible weighs 23.467. The mass of the crucible and hydrate weighs 25.785. I subtract the weight of the crucible weight. That gives me 2.318 grams for my hydrate. That's how much my hydrate weighs. Now, my hydrate's in my crucible. I'm going to heat it up. I'm going to drive all of the water away. And I'm going to let that crucible cool down, and I'm going to weigh it again. The second time I weigh it after heating, I get 25.164 grams. I subtract the weight of the crucible. That gives me 1.697 grams of my anhydrous. Just like last week, to find the weight of my water, I subtract the weight of my hydrate and the weight of my anhydrous, and lo and behold, I get my weight of water. Up to this point, we're doing the same thing we did last week. Now, we're going to do a silly thing. We're going to do a very, very silly thing. We just made all that effort to drive all the water away from it. Now, we're going to add water to it. So what we're going to do is we're going to quantitatively transfer all of the brown crystals from the crucible into a beaker. And we're going to wash them out. We're going to make sure we get every little bit of those anhydrous crystals back into a beaker. And we're going to fill it with water. And we are now going to take my solution, which has iron and bromine in it, and I am going to react it with aluminum wire. Guys, I have aluminum metal reacting with an ionic solution of iron bromine. What type of reaction is that? A nickel metal with the salt. What type of reaction is that?
Chemical.
Thank you very much. Oh, you're going to weasel out of this, aren't you? Yes, it's a chemical reaction. But what kind of a chemical reaction?
Hydrate or anhydrous?
Ionic?
Come on.
Single
Would it be a
displacement.
displacement?
Whoa, I heard it.
Single displacement.
A single, you remember those terms, guys? You remember that term? Single displacement?
Mm-hmm. Yeah.
Okay. Single displacement. Anybody remember the Flintstones? You know the Flintstones? You have Fred and Wilma and Barney and Betty. You remember those guys? Oh, you guys are too young. Nobody remembers the Flintstones?
I do.
Yeah.
I do.
All right, we have two couples. We have Barney and Betty, and we have Fred and Wilma. Well, Fred's out stagging around one night, and he happens to go to a bar, and he happens to go over and see, Betty's over there with Barney. I kind of like brunettes, so I'm just going to go over there and push Barney away. So I'm going to hook up with Betty now. And poor Barney is off in the cold. Okay? Madison.
I'm here
Hi. You ever dump anybody?
all the time.
There we go. Great. Good attitude, right? You're with
Yeah.
somebody and you see somebody that's hot over there. So you just throw this guy to the curb, run him over with the bus, and you're with the other guy, right?
Easy.
There
Yeah.
we go. Absolutely. That's all a single displacement reaction is. In this scenario, aluminum is more active than iron. So the aluminum will replace the iron in the bromine. What that does is that makes neutral iron precipitate out as a solid. So what we're going to do, we're going to get a piece of filter paper. We're going to weigh the filter paper. We're going to do this reaction. We're going to get all of the iron to react so that all the iron is now a solid. We are now going to filter that iron so that when we're done filtering, we have the mass of the iron and the filter paper. We're going to dry it, but we're going to have the mass of the iron and the filter paper. We're going to subtract the paper from it. That gives us the mass of our iron. We have our second mass here, guys. We have our water mass. We have our iron mass. Now, all it's going to take is for us to get the bromine. Do we have enough information to get the weight of the bromine? Nobody's read the lab, have you? How are we going to get the weight of the, let me ask you a question. What does the anhydrous iron bromide consist of? Come on, give me all the elements that anhydrous iron bromide has in it. How many elements are in that compound?
4 or 3.
Different ones. How many irons do we have? Right? We have
One.
iron. What else is there?
Bromide.
It's iron bromide. We have iron and we have
Bromide.
Thank you, God. There's a voice in the wilderness. Thank God. All right, so remember, the anhydrous has had all the water taken away. So the only elements that are in the anhydrous are the iron and the bromine. If I have the weight of the anhydrous and I have the weight of the iron, can't I get the weight of the bromine? Very easily. My anhydrous salt weighs 1.697 grams. I subtract the mass of the iron I just came up with. This gives me my mass of my bromine, 1.376. I have all my masses. Step 1 is done. Like I said, step 1 is the hardest one. Now, step 2, I have to change all those masses into moles. So I have my 0.321 grams of iron. Handy dandy, I got my 1 mole per atomic weight of iron. This gives me 0.00575 moles of iron. I take my grams of bromine. I multiply that by 1 mole over the atomic weight. I get 0.1722 moles of bromine. Second step done. Third step, I divide the smallest into itself. So in this case, iron is the smallest number of moles. I divide it into itself. That gives me 1. I also divide it into bromine. This gives me 2.99. Right now, I have the molar ratio. Right now, I have the value of the subscripts of my empirical formula. My empirical formula is iron, 1 subscript, Br3. Okay, we're doing the same thing with our moles of water. We got 0.621 grams of water. We're going to multiply that by the molar mass of water, which is 1 over 18.02. This gives me 0.0345 moles of water. I divide by the moles of iron. This gives me 5.99. This means there is a 1-to-3 ratio of iron to water. So my overall formula, FeBr3.6H2O. Questions, ladies and gentlemen? Are we good? All right. This is an important slide. When you are dealing with the ratio of the elements, if the ratio between the elements is a fraction, you keep multiplying that fraction by integers until you get whole numbers. This was step 4 of the empirical formula. However, you have to understand something about the ratio of the water to the salt. The salt always has a coefficient of 1 in front of it. It can't be greater than 1. So if you get a fraction for the comparison of the mole ratio of the salt to the water, you round it. When you're comparing the molar ratio of water to salt, you round it. When you're comparing the mole ratio of element to element, you multiply by integers. And that is because the elements, when you're comparing them, they can be more than 1. But when you're comparing water to the salt has to have a coefficient of 1. Problem. I got 2.65 grams of aluminum sulfide, .ZH2O. I heated it, reweighed it at 1.391. The anhydrous compound was placed in water and sodium was added. 0.500 grams of aluminum was recovered. Okay, so I have my aluminum, divide that by my molecular weight. This gives me moles of aluminum. My weight of water is my hydrate minus my anhydrous, which ends up being 1.234 grams of water. Divide that by 18. This gives me 0.0684 moles of water. Okay, to get my sulfur, I take my anhydrous weight, subtract out the weight of my aluminum. This gives me 0.891 grams of sulfur. divide that by the atomic weight of sulfur, I have 0.0278 moles of sulfur. Comparing the elements, moles of aluminum divided by moles of aluminum gives me 1. Moles of sulfur divided by moles of aluminum gives me a ratio of 1.5. So I'm going to start multiplying by whole numbers until I get rid of the fraction. I multiply the 1.5 by 2, I get 3. If I multiply the 1.5 by 2, I have to multiply the 1 by 2. So I ultimately get a ratio of 2 to 3. So my ratio of aluminum to sulfur, my subscripts are Al2S3. All right. Next thing I'm going to do is I'm going to take my moles of water and divide it by my moles of aluminum. I divide my 0.0684 moles of water by my moles of aluminum. I get 3.6. Remember, the aluminum sulfide always has to have a 1 in front of it. So I can't multiply it by an integer. The bottom one, I'm going to round. 3.6 is close to 4. So my overall answer would be Al2S3.4H2O. Okay. Ultimately, the procedures. By the way, ladies and gentlemen, please do not copy the objective directly from the laboratory manual. Put it in your own words. I don't know how many times I saw the percentage, whatever, the precise percentage, whatever the wording was, you guys kept on spitting that out. Reword it, please. Reword the procedures. Do not cut and paste the procedures into your notebook. That does not count. I want you to redo the procedures in your own words. All right, so what are we doing? We're going to weigh a crucible. We're going to weigh the crucible in the hydrate. We're going to heat it gently. If we heat it too hard, it's going to decompose. We heat it, we're going to let it cool. Then once we let it cool, we're going to weigh the crucible and the anhydrous. The nice thing when we do this experiment, the anhydrous compound is brown, the hydrate is green. So you know when you're done. Okay, so we have weighed the hydrate, we've weighed the anhydrous, we now have the water weight. Now we're going to add water, and we're going to quantitatively transfer things from the crucible into a beaker. Generally speaking, you want to add about anywhere from 2/5 to 3/5 full of the filled with water. We're going to coil an aluminum wire and we're going to put it into a beaker. Amazingly enough, the reaction starts almost immediately. Now, the solution is blue. Okay? Solution is blue. Where is the blue color coming from? Let me ask you a question. We put copper chloride into solution. Does chloride have any color? Salt water. You guys have all put salt in the water. Salt water is sodium chloride. Does salt water have any color to it?
No.
So, can the blue color be coming from the chloride?
No.
Nope.
Where's the blue color coming from?
Copper.
So when the blue color goes away, your reaction's done. Generally, it takes about 40 minutes to an hour. So we have our reaction, our single replacement reaction. Our aluminum is replacing copper, and we are plating out our copper. The next step, we add hydrochloric acid, and the hydrochloric acid is to make sure that the aluminum chloride stays dissolved. We weigh a filter, and we knock off all the brown solid from the wire, put it in the solution, and we knock it all off with a glass stirrer. Why don't we use iron? Why would we not want to use iron? Is it possible it could react with the copper? And instead of plating out copper, we would be plating out iron. So you want to use a glass stir rod there. We're going to use suction filtration, and the copper is going to get filtered through the filter paper. We're going to squirt ethanol to get rid of all the water. We're going to put the filter paper onto a watch glass. We're going to dry it, and we're going to weigh the copper and filter paper. We've already weighed the filter paper. Subtract the two, we have the weight of the copper. Take the weight of the copper, subtract it from the weight of the anhydrous, we have the weight of our chloride. That's it, guys. Any questions? Any questions at all, guys?
That is what we're gonna do in the lab, right? That's basically what it's going to be.
I've gone through everything. It's Victoria, right?
Veronica.
Veronica. Sorry, I'm seeing Santiago there, and it's throwing me.
I'm
Veronica. Okay, Veronica, I've just gone through all the procedures of the lab. I've kind of described what the lab is going.
Just there's one thing that I still a little confused when it says the mass of, when it's asking for the mass of, does that mass we get it from the periodic table, or?
Are you talking about the atomic weight?
No, like in the lab, when we're gonna do the stuff, the calculated data, it says mass of the copper, mass of water.
Okay. Veronica, I've just gone through that. Okay.
Okay.
Let me see. Let me see if I have it somewhere. All right. I'll have to use my iron example. Okay, Veronica, you're going to do this the same way. Okay? How you get the masses. You are going to need the mass of the hydrate. You're going to take the mass of the crucible, subtract it from the crucible and the hydrate. This is before heating. If you subtract the crucible and hydrate and the crucible, you get the weight of the hydrate. Okay, Veronica?
Yeah.
The next thing you're going to do, the crucible gets heated up, and then you're going to weigh the crucible and the powder after heating. The powder after heating is the powder without water, or the anhydrous powder. I subtract again the crucible from the weight of the crucible and the anhydrous. This gives me the weight of the salt without water.
Yes, I'm good in that part.
Okay, so I got the mass of my water. Okay, Veronica? Now we're going to go and we're going to do our reaction. We're going to do our reaction, and the aluminum is going to replace the copper, and the copper is going to form a solid. Okay, Veronica? Veronica?
Yes.
You're not sounding confident, Veronica.
I mean, I understand the part where the product is like it changes. I know that. It's just it throw me off in the calculations.
Okay, Veronica. We're doing the reaction, right? We're doing a reaction. We have solid aluminum. We're putting it in a solution of, in this case, iron bromide.
Mm-hmm.
Okay. So we get the reaction. All of the iron bromide reacts and makes aluminum bromide, which still stays in solution, but our iron is a solid now. So now what happens in the experiment? I weigh a piece of filter paper. I filter the iron water through the filter paper. Iron stays back on the filter paper. Okay, Veronica? So now all I have to do is subtract my filter paper from my mass of iron and filter paper. That will give me my mass of iron. Okay, is that good? Do you understand that one, Veronica? Okay. Now, you have to realize that the anhydrous salt of iron bromide consists of just iron and bromine. That's all it does because the water is driven away. The only thing that's in the iron bromide now is iron and bromine. So if I know what the anhydrous salt weighs and I know what the iron weighs, if I subtract the iron from the anhydrous iron bromide, that gives me the weight of the bromine.
Okay.
Are we good with that now?
Yes.
Okay. So once we get to that stage, we've got the bromine weight, we have the iron weight, and we have the water weight. Next step is to turn it from grams into moles. We do that by multiplying by 1 mole over the atomic weight. And I get 3 separate amounts of moles. I compare the iron to the bromine. I take the moles of iron, which is smaller than the moles of bromine. I divide it into itself and I get 1. I divide it into the larger number of moles and I get 2.99. This means my molar ratio between iron and bromine is 1:3. The molar ratio is the subscripts. Subscripts are the molar ratio. So if it's 1:3, then when I write my formula, my iron has a subscript 1, my bromine has a subscript 3.
3. Okay.
Why does it sound like you're not very confident here, Veronica?
No, I am. I mean, it makes sense. The steps are making sense now. I just gotta do
Okay.
them.
There is, if I haven't posted the PowerPoint, I will be posting it. And they take you through a calculation in the lab manual. All right, anybody have anything else on this lab?
Can we just go through the
Oh,
results?
have I gotten you guys? So I've gotten you guys. I'm. This is a crutch now, guys.
You spoil us.
Yeah, what can I tell you?
Well, on the last one, you gave us that 45 for the first answer, which we wouldn't have known. So I just wanted to make sure.
Back. It's fairly straightforward. Okay, course content. I would, if I were you, I would expect the post lab to be a little more rigorous than it's been. All right. Are you seeing my my computer, aren't you?
Yes.
Okay, start quiz. Mass of the hydrated sample. Just show me you're going to take the weight of the crucible and subtract it from the weight of the crucible and the hydrate. Mass of the dehydrated sample, same thing. Dehydrated means the same thing as anhydrous. It's the amount of the sample without water. Mass of the copper. Basically, that is the filter paper minus the filter paper and copper minus the filter paper. Moles of copper, you take the grams of copper, divide it by 1, or you multiply it by 1 mole over the atomic weight. Now, guys, remember, when you're choosing an atomic weight, remember you do not want to let your atomic weight limit your sig figs. So if your weight is 3.164, 3.164, that sounds right. That means it has 4 sig figs. That means your atomic weight has to have 4. All right, mass of water evolved. Simple enough. Mass of hydrate minus mass of anhydrous gives you the mass of water. Divide that by 18.02, you get the moles of water. Mass of chlorine. Anhydrous sample minus weight of copper equals weight of chlorine. Multiply the moles of chlorine by 1 over 35.45. This is important. Mole ratio. I want the rough mole ratio. You're going to take your moles of chlorine and you're going to divide it by your moles of copper, and you are going to have a rough ratio. It may be something like 2.09 to 1, 2.25 to 1. In this particular box, I want to see that rough ratio. You're going to also do the mole ratio of water to copper.
Did you want that
Again.
ratio? Did you want that ratio for chlorine and copper to be reversed as well? Or do you want to keep it? Because that's how it was in the quiz that I got wrong.
As long as you make it clear what's the copper and what's the chlorine, I don't care which way you put it, okay?
Okay.
I disagree with this. I disagree with the way he's done this because he's confused the snot out of you is what he's done. Just make it clear what's the ratio. In other words,
Okay.
okay, fair enough?
Fair enough.
Okay, same thing. I want the rough molar ratio for water to copper. And that's it. Exit preview. For kicks and giggles, let's go and do the post lab. What am I doing? I'm losing my marbles. If anybody finds my marbles, would you please go and return them to me? I missed them. You know, I had a great thing. A friend of mine, when I was working in Dade County Crime Lab, he lost 1 kilo of cocaine, right? Lost 1 kilo of cocaine. So the attorney is very, very upset about this. And he's just beside himself. And my friend just calmly says, "Oh, it's not lost. It's in the process of being found." He got away with it too. What am I doing? Oh yeah, I'm starting quiz. Somebody's got to keep me on track here, guys. Okay. In a certain compound of copper and oxygen, we find that a sample weighs 0.8120 grams containing 0.4425 grams of copper. How many moles of copper are in there? Okay. We find that we have a sample that contains, the sample weighs 0.7308 grams of copper and 0.4428 grams. I'm sorry. The whole sample weighs 0.7308 grams. The copper weighs 0.4428. How many grams of oxygen are in there? If you don't know how to do this, speak up. All right. Now we have that same sample. We have that same, we have different numbers. Sorry. Be careful. Be careful when you're going through here that you're not thinking they're the same numbers from question to question. The value's different. Okay. So for the third question, we have the sample weighing this much, the copper weighing this much. It wants to know how many moles of oxygen there are. So you got to subtract the 2 and you have to divide by 16. Notice this something, guys. Isn't there a whole lot more copper here than there is here? Do you see those gram weights? Are we dealing with the same formula of copper oxide in both equations? Probably not, guys. That's another thing he likes to do. All right, third question. All right, we have the atomic masses given to you, and a compound is found to have this many grams of X and that many grams of Y. What's the molar ratio? You got to take this number, divide it by that one to get moles. This number divided by this one to get moles of Y. Find out which one is smaller and divide it by the smaller number. This one, you got grams of carbon, grams of water. Figure out the mole ratio of carbon to water. You're going to get the moles of carbon and the moles of water. You're going to divide the moles of water by the moles of carbon, and you get an answer. Easy peasy, guys. This one's not even that hard. Are we good?
Yeah.
The all the data will be in the where we all find the other numbers.
Yep. It's in the same place as it always is.
Okay.
And that's another thing, guys. Some of you have been looking on the videos and taking the numbers from the videos. That is not where you get your data. Getting the data, go to control course content, take it down to where it says student data for labs. Click on that, go back up, open it, and it'll take a few minutes to open. Scroll down. That's the Hydrate lab. Now comes the Empirical Formula Lab, and that's all the data you need. Anything else, ladies and gentlemen? Kara wants to get out of here. Kara, do I have a vote to adjourn?
You have my vote.
Do I need a motion, guys? We
I
got
have
to
a
do
question.
Robert's Law of Order. Do I have a motion to adjourn?
I have a question on last week's stuff.
Oh, man, Brian, you're
I
keeping us
just
here.
remembered. I just remembered.
Okay, guys, you're free to leave. That's all I have to do tonight, all right? You're free to leave if you want to stay and listen to Brian pander to me.
I have questions for you for the book.
Okay, Veronica, just wait until Brian gets done, okay? All right,
Yeah.
Brian, you have the floor.
Alrighty, it's on the results assignment from last week.
Okay? Do you mind if I show other people? If you do
No,
mind,
I don't mind.
I'm gonna have to wait until everybody gets out of here.
No, it's fine. You can show it.
Okay, we're talking about the Hydrate results, correct?
Yes. So that
You're easy to find anyway. I know where you're at.
last one.
Last one. Okay, now what question?
It'll be the first and last questions.
The first and last questions. Okay, Brian, you're looking for more points, right, Brian?
Maybe.
All right. Are you going for, is this going to be a double or nothing? If you're right, then I change the points. If I'm right, you get a 0.
Oh God, no.
All right, first question.
All right.
Oh, I haven't even graded these yet, have I? Is this
don't
one that
think
Brian, is this the one you just turned in?
Yeah, I think it's wait, is this the results one or is this the post lab? Hold on, let me.
No, this is the results for the hydrated
Oh,
salt.
I'm sorry. It was the post lab. I'm sorry.
Oh, now it's going to be, now you're asking me to go back and open another one?
Yeah, I'm sorry.
Okay.
Now, can I ask a question about that? There was one question, I don't remember if it was the results of the post lab that he asked. What was the name of I guess it was the little container where they were showing the chemical? Isn't that the letter A? Or was that what Brian said that you gave us?
He said it was 45 during
Oh,
class. I don't know why.
are you asking what the unknown number is?
Yeah.
Veronica,
Yes.
642.833. Put any number there. You're going to get credit for it.
I put the letter that it went in the video. I didn't know.
Anything but the letter. If you put the letter, then you don't get points for it.
Yeah, I put the letter that was in the video.
Veronica, you're getting points. Don't worry about it.
Okay.
Brian, does it matter which one?
No, because I got it wrong in both of them.
Okay. All right.
So that one, I
It's
got.
a pot.
So when I did it, the first number is less than the
Yeah, but
experimental.
do you see these do you see these things here, Brian?
Oh, absolute value, of course. Dang it, I didn't see that. All right, that's my fault then. Sweet, thank you. And then it's the last one. I couldn't figure out how to figure out the number of hydrogen.
Okay, wait a second. Okay, so, oh man, you're gonna make me do the whole problem.
I think I have it written out.
All right. Okay, I just need a sheet of paper. I need a calculator. Okay. All right. I got 39.9047 minus 34.9579. That gives me 4.9468 grams. That's the hydrate weight, correct?
Yeah.
All right. So.
And then the anhydrase.
37.3397.
2.381.
Minus 34.9579 equals 2.38.
Yep. 1 8.
1.8. That's the weight of the anhydrous.
Mm,
So the weight of the water is going to be
2.56.
4.9468 minus 2.38. 4.9468 minus 2.3818 equals 2.565.
Yep.
Okay, that's the weight of my water. All right, now I got to sit here and okay. All right. Okay, so you have a mass percent.
Yes.
Okay, so the mass percent is going to be 2.565 divided by
4.9468.
this gives me 51.85%.
Yep.
All right, now you have to realize that you're going to have to do a bunch of calculating here. It's the only way I know to figure this problem out.
So I'd have to go through 6 from 18, and then I have to
You
go
got
all
it.
the way through.
Well, you can figure it out.
Yeah.
What I would do
know.
is I would do something like maybe 10 through 14.
Okay.
All right, let's do 10. All right. If my NO3 taken 3 times is going to be 14.01 times 3 and 16 times 9. Guys, if anybody's sticking around for this, is it just Veronica and you, Brian?
Yeah.
Veronica?
I was just wondering if there's a shorter way instead of doing every single one of them.
Well, there kind of is. But you got to realize what you're doing. Okay?
I got that one wrong too. I didn't know how to do it, so I put any number.
That generally is the way. I got I got 223.31 as the weight of my salt portion. Okay?
Okay.
All right. Now, yes, there is an easier way to do it. Okay, that's the weight of my salt portion, right? Brian?
So you don't include the H2O part. You just do the.
No, just bear with me for a second.
Okay.
All right. So I know that 51.85% is the water. Is the water portion, right?
Yeah.
So that means that 48.15 is the salt portion, correct?
Yeah.
Okay. So if I do 51.85% of X is equal to 223.31. Because, I'm sorry, wrong. Sorry. 48.15% of X is equal to 223.31. Do you see what I did, Brian?
Where did you get the 223.61 again?
Because M weighs 37.28 and 3 nitrates weigh 186.03.
I thought it was 4203.
4203 is the nitrogen.
Oh, you're doing it together. That's right.
I'm
Okay.
trying, what I'm doing is I'm figuring out the molecular weight of MNO3 taken of the anhydrous portion. Okay. And NO3 by itself is 48 and 14.01. That is 62.01. That's what NO3 is. If I have three of them, they're worth 186.03.
Yeah.
To that, I add the weight of the atomic weight of the metal, which is 37.28. That's how I came up with the 223.31. We good
Got
with
it.
that?
Yeah.
Okay. I did the weights that were given to us. I did those weights and came up with 51.85% of water. Okay, Brian?
Mm-hmm.
So if 51.85% is water, that must mean that 48.15% is the weight of the anhydrous salt.
Okay. So then I just multiply it by the 0.48.
Now, I got multiplied 48.15 times X is equal to 223.31.
Okay.
You wanted to do it, you wanted to know how to do it faster.
Yeah. So that would give me
463.78.
Okay.
So that is the weight of the hydrate. Okay?
Mm-hmm.
If that's the weight of the hydrate and I subtract the weight of the anhydrous from it, which was 223.31, this gives me the weight of water is 240.47 grams divided by 18.02, and I get 13.3. That's the X that's in front of the water.
Divided by 18.2.
Yeah, 18.02 is the molecular weight of water.
Okay. Oh, okay. Got it.
So that's the quick way to do it.
That makes sense.
The non-quick way is to, okay, plug in 10 for the
Yeah.
waters, figure out what that mass percent is. Then you would do 14 for the waters, figure out what that mass percent is. And you would eventually realize that the 51.85 is closer to 14 than it is 10. So you say, okay, well, let me try 13. And 13 would be almost dead on. So that's the long way to do it.
Yeah. That's the way I was trying to do it, but then I guess I messed up and then I forgot I forgot to split my oxygen and hydrogens. Like, cause I was adding all of it up and then dividing all of the oxygens and hydrogens by the total mass of the hydrate. Yeah.
It's not, this is not an easy question.
Yeah.
It is really not an easy question. And it's kind of a thinking, literally speaking, Brian, you didn't notice it, but I was going through about 3 different ways on how to solve this when the final way just came to me. Okay.
Okay. All right. That was it.
Okay.
Thank you. Have a good night.
Veronica, do you take care, Brian? Veronica, what can I do for you?
About the notebook.
Okay, let's go. Let's go for that. Last one I have graded will be the density one, I believe.
Mm-hmm.
Okay, so I'm going to go back. Okay, and I think you're the only one in here. Yeah,
Yeah.
it's just you. So and your last name, Veronica.
Bruseno.
Okay. Okay, when I. Why is this not doing that? Oh, I didn't hit the little box. Let's try this. Yay. Okay, when I do this, I get little yellow boxes. Okay. So, little yellow box, be more succinct. In other words, be shorter. Okay. All you need is one sentence, Veronica. Like, what do you think we're doing today? What's the overall objective for the experiment we're doing today?
We're looking for the mass of the copper to see
Is
which
that what we're ultimately determining? What are we ultimately determining?
we are determining the
Look at the title. What's the title of the experiment?
empirical formula,
So what are we trying to find?
the atoms,
No, what's the title tell you you're trying to find?
the empirical formula.
We are to determine the empirical formula of a hydrate of copper and chlorine. To see how simple and sweet that was?
Okay.
There are a couple of things you can do. You can look at, generally speaking, the lab manual will give you a little bit of synopsis. It'll give you a little hint as to what you're doing. Plus the title will give you one. So what I want you to do here, one sentence, that's all you need is one sentence. To find the empirical formula of a copper chlorine compound that's a hydrate. That's all you're doing, okay?
Okay. For the procedures, I shortened up this time, and then
Okay,
I guess it was too much short.
I need you to be specific, okay? Veronica, what you want to do is your procedures that are in your notebook. You should be able to hand your notebook to anybody off the street, and they could take that notebook and literally follow what you've written and repeat your experiment. That's ideally what the procedure should do. Volume measurement of two objects. Simple enough. Use a ruler to take measurements of the length, width, and height of an aluminum bar.
Okay.
That's simple. That's all you needed to do for that. Okay. The volume of a glass sphere. You're going to have to fill a graduated cylinder. First of all, you're going to have to weigh the sphere because you want to make sure it's weighed before you get it wet. You are going to put a known volume into a graduated cylinder. I don't care what it is, 15 milliliters. You want to say 15? Put 15 milliliters of water into a graduated cylinder. Tip the graduated cylinder, slide the glass sphere so that you disturb the water as little as possible. Read the new volume.
Okay.
You understand what I mean by be specific?
Yes.
That's what I'm talking about. Okay? And this is gonna, okay, this works. Even though I'm not happy about the calculations, but the data table worked fine. All this is working fine. This is working fine. Where are your calculations?
So in the graph, I think the paper of the graph, it says at the top to put it in the graph. That's why I put it inside.
Okay, well, all right, that's fine. That's the slope. Where is the calculation for the density of your aluminum bar? Where is the calculation for the density of your sphere? Where's the calculation for the waters? You only had to do trial 2, but where's the calculation for the density of trial 2 for the water? Those all have to be in here, Veronica.
Yeah, so the density, the volume, the
Again,
density.
there it is.
They're
It's
there.
right- yeah, right, they're right there. Where are they though? Are
Yeah.
they in the data table or are they in their own separate section?
No, they are in the data table, yeah.
Okay? I'm gonna break you of that habit before the end of the year. And this, you didn't give me an error analysis.
What
And
is,
an error analysis is something that you had control over or didn't have control over. For example, all right, as you slid your sphere into the volume, some of the water drops splashed up on the sides of the graduated cylinder. All right,
okay, so it changed the,
it changed the volume. You have less volume in there than you should have. Okay, because the water splashed out. So if your volume, you have to cite what the error is. Then what you have to do is you have to find out, you have to figure out how that affected your results. By the water splashing up on the sides, the volume was less than it should have been. If the volume was less than it should have been, then my density was greater because I'm dividing volume into mass. That would have meant that my density was bigger than it should have been.
okay,
All right,
all right.
Veronica, you're going to get through this. I swear to God, you will. And
No, then
I
I
don't
think
care.
great for the next one though. I already know the next, like for this third lab that we did, I already know the grade because I got the same mistake in the objective. The procedures, I got the same thing. So
Okay. Then look at it this way. You're not going to be surprised. But Veronica, remember, I promised you, even if it takes you until the thin layer chromatography lab, and that's got to be a good 7 labs down the road, even if it takes you that long to get it right, I will go back and make all of those lab reports a 9.
okay,
I can't be fairer than that.
okay. Just I want to get it right.
I understand you're frustrated, and that's why I agreed to stay after class and talk to you about it, okay?
I appreciate it.
No problem at all.
All right, I'll do this one with
You're
the stuff.
gonna do this one with the right stuff. The one that you turn in next week is gonna be great. Okay?
Thank you, Professor. Have
You
a good night.
You have a good night.